Audio okay. Looks like it's okay. As promised, back for the second half of the cosmology. So we'll be finishing up the chapter 3. We'll see how that goes. Thanks to all who were here yesterday. And the topic will be starting with Newton. Let me get my. You already recall yesterday we talked a little bit about uh, Catalan transformations. Talked about the difference between the relativity and Newtonian conceptions of gravity. So basically, we'll be continuing with the Newton's perspective more so and going from there. So, as before, the book that I have now is a paper book, so it's not actually in able to show digitally. But I'll write out and show y'all what I'm writing in my on my pad, starting with chapter 3.3. So we might go into the regular time a little bit, see how long it takes. It should be visible now. See what we have. There we go. So right now we're on 3.3, general relativity, and we'll keep the party going. So let me, like I had my window a little smaller last time or something. Let's see what I did. Be sufficient. So let's see what we have. Now, like I said yesterday, this part is actually slightly heavy in math, uh, but it has some good concepts as well. So the way of Einstein, general relativity. So last time we talked about special relativity. So this would be the general conception. And let me know how the audio is. If there's any issues, seems like it's fine on my end. And it looks like the stream is clear enough. Let me know if I should adjust it more or something like that. Maybe I'll move the book title over a little bit. Maybe shrink it down just a little bit. See if that helps. Right? So it says the theory of special relativity has limited usefulness. So SR. We spoke yesterday about how Newtonian has the limits of when we're close to a large potential, so we're near a very large potential, like a large gravity well, or as Einstein would say, a very large curvature in space-time, then Newtonian and Einsteinian relativity and classical dynamics won't give the same answer. But in the normal cases, like on Earth or in space and not near a large gravitational field, when F equals ma is the same in all frames, then either one will work. They'll give you the same answer. Uh, and this is generally special relativity we're talking about here. So just like how, and if you recall, Mercury has a precession of its orbit, and it was able to be worked out from relativity, even though I don't recall exactly which one. But maybe we'll talk about that here. But it deals only with cases where gravity is non-existent. It took Einstein a decade from 1905 to 1915 to generalize his theory. Interesting. So he started with SR, no gravity, which was for inertial frames. In 10 years, he worked to generalize it. So this works with even uh, non-inertial frames, as my relativity professor was saying. And if you hear, be sure to drop a line. Let me know if there's any questions or comments. It took it to see how Einstein was inspired by the equivalence principle to devise his theory of general relativity. Let's begin with a thought experiment. And the equivalence principle, we spoke about that yesterday a bit, should be the fact that the two masses are the same. So basically, we have the mass of F equals ma, like the mass that causes acceleration. They call that the inertial mass, and the mass that causes things to attract to each other, they call gravitational mass. And apparently, there is a very slight difference, like we are talking about yesterday, between these two, but the difference is so slight that we consider this an equivalence that mi equals mg, because the difference is so minuscule as to not have any effect on anything. So this small difference to the point of exclusion is what he utilized. Let's begin with a thought experience. Suppose you wake up one morning and find that you have been sealed up, bed and all, with an opaque, soundproof, hermetically sealed box. Startled by this realization, you drop your teddy bear. Observing the bear, you find that it falls towards the floor of the box with an acceleration of 9.8 meters per second squared. At the moment, a window on the side of the box reveals that you're inside an alien spaceship that has been accelerated at 9.8 meters per second squared by a rocket engine. When you drop a teddy bear or any other object within a sealed box, the equivalence principle permits two possible interpretations, with no way of distinguishing between them. Either the box is static and gravity is pulling it down, or the box itself is being propelled and acceleration is going on. The behavior of the bear in each case is identical. In each case, big bear falls at the same rate as a little bear. In each case, a bear stuffed with cotton falls the same rate as a bear stuffed with lead. In each case, a sentient anglophone bear would still feel weightless. Right? So all things will fall at the same pace. Same acceleration, regardless of content, what it's made of, regardless of size, uh, and everything will also be weightless or experience weightlessness during the fall. This is why when you actually calculate uh, the equation that we spoke about yesterday for G, when you basically pack uh, both the masses together, F G and Fa, the force of acceleration and the force of gravity, and you end up getting the 9.8 meters per second squared. I thought I wrote that down somewhere. Here it is. When you solve for this equation, that's why in the equation the small masses cancel out, and all you have left is the mass of the Earth, because all things fall at the same pace in the gravitational field, and this is consistent with the fact that things that fall in the gravitational field is consistent with. Uh, hey, what's going on, Lisa? How you doing? I know Biggie. I know I'm starting earlier today because I may go a bit longer, so I may still be here until 9. I have 10 pages left, really. 10 pages of the book left. So we did 10 pages yesterday. I'll do 10 pages today. I don't expect to get a phone call or anything, so it'll be straight through. And actually plan on going through the stream yesterday and cutting out the phone call period. I took a little break in the middle. So yeah, so a little bit earlier today, so I know it'll be a long one. So I got to read this book here for my cosmology class to do the homework. I got an A on the first homework. I just got my grades back today. Maybe I might even review some of those assignments questions for y'all, was complicated. Like calculating how far, uh, like why the universe is not all light, and calculating the distance that we can see in the universe, given the density of galaxies and stars in the universe. And it got to be complicated. I need some help from my TA for that one. So maybe I'll review some of that in future weeks. Hopefully, if I manage to get an A and everything, I'll graduate with an A minus. So it is looking a little bit doubtful. Like it was looking doubtful in my quantum homework for a little while, but I pulled it through to the end. Still don't know if it's going to be an A, but it's going to be at least decent for my second homework. So I'm gonna have to study that. I've been focusing on my research. I have to turn in my abstract tomorrow for the presentation I'll do in at the conference in March. So I was focusing mostly on the weekend on that, but I still have to get other things in. So once I finish reading this, I should theoretically be able to do the chapter 3 homework, see how that goes. So just reviewing how mass, the equivalence of mass, whether something is falling in a gravitational field or if something is being accelerated by a force like F equals ma, all things fall at the same pace no matter the size, which is why when you derive this equation like I did in that debate that time, and I think even on the screen, while the two little masses are canceled, and all you're left with is the mass of the Earth, because ME and mg are equivalent, the inertial mass and the gravitational mass are equivalent, and thus all things fall at the same pace no matter the size or what have you, so the small mass doesn't matter. And that's what they're pointing to as far as one of the things, ironically, that motivated Einstein or prompted him to be able to generalize his special relativity because these masses are equivalent. This is what they're saying. Einstein's insight, starting from the equivalence principle, led him to the theory of general relativity. To understand Einstein's thought processes, imagine yourself going back in a sealed box, being accelerated through a planetary space at 9.8 meters per second squared. You grab the flashlight that you keep on the bedside table and shine a beam of light perpendicular to the acceleration vector. Right, so they're saying that you're in the box is being accelerated, and now you have a flashlight and you're shining light horizontal to the direction of acceleration. So acceleration is still going like this at 9.8 meters per second squared, just like you're on Earth. So let's see what they're saying here. Since the box is accelerated upward, the path of the light beam will appear to you to bend downward as the floor of the box rushes up to meet the photons. That makes sense. However, thanks to the equivalence principle, you can replace the accelerated box with a stationary box experiencing a constant gravitational acceleration. Since there is no way to distinguish between the two cases, we are led to the conclusion that the path of photons will be curved downward in the presence of a gravitational field. That is neat. Gravity affects photons, Einstein concluded, even though they have no mass. Damn, that's deep. So what he's saying is, since the equivalence principle is a thing, so let's say we model these photons as, model the light as photons, as these little particles of light that's shooting out like a BB gun. What's going to happen is, since we're accelerating up, the box will have moved up before the light hit the other wall. So if we were to be able to measure it precisely enough, we will see that the light seems to be falling down against the wall. Of course, I'm exaggerating it. Ironically, it brings up one of the experiments. I'll let y'all know I will be a learning assistant in the modern lab. And there was a group doing my favorite experiment, measuring the speed of light. That was my favorite one out of the whole lab, I think. And I was helping them with it. And of course, they were going down the hall and back, bouncing the light off a mirror. But even then, it wasn't an appreciable drop. So, you have to have a precise instrument, I'm sure, to measure this, or have a very big gravitational field. Like, you know, Einstein rings, where you can have like a large massive body here, and we can be seeing, for instance, multiple images of a galaxy on the other side of the large gravitational field because it's bent around. So that would be what Einstein was talking about. If I also look at this from the side, if I also turn this thing sideways, I mean, when they want to use it to try to support their position, then it's real. Of course, they just believe what they want about it. Like in the debate that I had with Allen and Toby, they was trying to use the Milkers and Morley, but they was ignoring the fact that the paper itself says the Earth and the solar system moves. I pointed that out in the debate. They couldn't touch it. And I heard, uh, was it Allen on the after show on Witz's channel saying he didn't even read the whole thing. He didn't even read that part all because the part where they were making it clear that the solar system moves, it was in the end. And he was saying I didn't even read that part. So, they just go and pick and choose and just when if they in their misunderstanding they think it helps them, then they just this is amazing. I don't get it. But I'm glad I don't talk to those people anymore. You probably won't see me debating anymore, by the way. I already let MDD know that I'm not really interested in even talking to these people anymore, especially seeing how they responded to the final experiment, especially seeing how that talk I tried to I mean, I knew he didn't know what he was talking about, but still he declared that I was being rude or something when I told him when we was in a debate. Clearly, is it that you're just repeating a meme or something? Oh no, I know, okay. So I brought him on to have an actual discussion, and he kept avoiding the whole time. I finally got him to actually give an equation and try to defend it. Then he just declared, "You don't know," and left. Apparently, he ran. So I was like, I don't even want to talk to these people anymore. They clearly don't know what they're talking about, and then they're just totally not honest about it the whole way. It's just a waste of time. And the fact that they to see what they did to Whitsitt and journalism, and then when they just pointed out, and Whitsitt is still a flat earther. He just pointed out that there is a 24-hour sun, and they just threw him under the bus. And journalism, of course, they did the same, but apparently he's not a flat earther anymore. So I don't know. I just don't. It just feels like a waste of time at this point, even though it was interesting for a while. But I may change my mind in the future. I don't know. But at this point, I've already let MDD know, and James was like, "Oh, cool. Just let me know if you ever want to come on for it with a different topic." But I'd rather just actually learn science rather than keeping up with all of their lies and misunderstanding. And that's why the conversation was so difficult with Fat because I was actually trying to have a conversation rather than doing like I did with Witsit, where I was just keeping track of all these lies and misconceptions. It's the only way you can talk to these people. Is just keep track of all the lies and misconceptions, and that's all it is. As it seems impossible to actually have an honest conversation with them. So I'm just not interested in doing that anymore, keeping track of these people's words and stuff. So I'll just do other things like learn science. And Lisa says debating is kind of a waste of your time and detrimental. Yeah, I would agree in the end. I mean, to a certain extent, I will say it's helpful, but that extent I think has passed. Um, that moment I think has passed. But I mean, there's a certain point. But I mean, like MC Toon and them. I mean, currently their interest in it hasn't waned at all. MC Toon was on somebody's channel just a little bit ago, and I mean on MDD just a little bit ago. And um, I saw FTFE, and it was a pleasure debating with him. He was debating again with that same whatever that guy's name is about the moon landing again. It's like, why are you doing this again? And after I had that debate, and again, it wasn't even supposed to be about that, but the topic changed at the last minute. I was like, cool, you know. And people were messaging me afterwards saying, Toon already destroyed this guy, and he's repeating the same points that MC Toon already destroyed him on. And I don't even know why FTE, but again, that's what FTE does. I mean, I guess if I did it for a living and that's what I made money doing, I guess it'd be different. But now it's just a drain on my time, really. And I guess I'm not really interested in it enough to put forth the time to actually build up enough. A lot of people might not know my first video, my first flat earth debunk video was in 2018. I've actually been doing this a while. It's just I haven't been consistent with it because after a while, I just get tired or burnt out and I go away for a while. And then I come back again like a few months later or a year later or something. It's just people, I guess, like that really enjoy it, like MC Toon and but few of them started. I don't know when MC2 started. I know another one that's coming to mind. The pilot, he started around that time. I don't know. I'll just continue doing what I'm doing. Lisa says, working on your degree is far more useful. MC2 does it for fun, and he's a good communicator. Yep. He says their phone algorithms won't change. That's the way it is. Um, Looking at this thing from the side, by the way, let's take a look at this eye here. This eye, by the way, is where we are in the Milky Way, right? So we're looking at something that's hundreds or thousands of parsecs away, very far. And in this case, from our perspective, actually, I drew it like this. Really, from the side perspective, it'll be like this. Oh, no, I drew it actually backwards. So it'll be the actual galaxy, or is here. So this is a galaxy that is far in the universe. A massive object is here. Let's say this is gargantuan, the black hole from Interstellar, a huge object. And in our vision, it looks like we're seeing six, let's say, galaxies, but we could study the light from them and see that they're all the same galaxy. And it's just the light is being bent uh, around this large gravitational well. So the light is hitting our eyes like this. And this is what the book is talking about right now. The fact that light bends relative to a gravitational field. And it the effect is the same whether it's actually a large gravitational field that's bending the light, or we're moving and sort of moving out of the way of a photon. So it seems to pass us up a bit behind where we were before. It's pretty interesting. I never really thought about that in detail, but this is why I'm not Einstein. However, thanks to the equivalence principle, if we replace the accelerated box with the stationary box experiencing a constant gravitational acceleration, it's the same, right? Since there's no way to distinguish between these two cases, we are led to the conclusion that passive photons will be curved downward in the presence of a gravitational field. Gravity affects photons, Einstein concluded, even though they have no mass. Contemplating the curved path of the light beam, Einstein had one more insight. One of the fundamental principles of optics is Fermat's principle. So to write this out, this is Fermat's principle. And Lisa says, I really didn't understand how a massless photon can bend until recently. Space-time tells how to move. Exactly. It short its path. And that's exactly how this, at least how the professor termed it. I know this book says it somewhere. Maybe I read it already in one of the previous sections. Einsteinian's perspective is space tells mass how to move, and mass tells space how to bend. So mass is telling space bend like this, and then when the mass moves, the space is telling the mass to move in this curved position, and then we have an orbit around a planet. Whereas um, Newtonian, this is Einsteinian, Newtonian would say that mass, uh, uh, what? I don't remember the exact way they worded it. Mass tells it's a force. I don't remember. I'll run into it, but I don't remember the exact terminology. But it's something like mass tells how to put a force, and the force tells mass how to move, something like that. Fermat's principle states that light travels between 2 points along the path that minimizes the travel time, like you were saying just now. Fermat's principle requires that the travel time be an equilibrium, either a minimum or a maximum to be specific. In most situations, however, the path taken by light minimizes the travel time rather than maximizing it. Interesting. So it sounds like they're saying it could also maximize the travel time, which doesn't really make sense because the I mean if you really wanted to maximize the time, you could just go back and forth across the entire universe like this, like micromillimeter by micromillimeter until you get to the end. So I don't. So I have to think about that one. In most situations, okay. In a vacuum where the speed of light is constant, this translates into the requirement that light takes the shortest path between 2 points. In Euclidean or flat space, the shortest path between 2 points is a straight line. However, in the presence of gravity, the path taken by having a presence of gravity, the path taken by light is not a straight line. Thus, Einstein concluded space is not Euclidean. The presence of mass in Einstein's view causes space to be curved. And this, in fact, in the fully developed theory of general relativity, mass and energy, which Newton thought of as two separate entities, are interchangeable via the famous equation E equals mc squared. Now, by the way, I asked my professor about this equation in class, anticipating speaking about it with you all, and I asked him, uh, "How is this known?" Because if you think about it, uh, I mean, of course, if you think about it from the fact that light is a universal constant, the speed of light, and y'all who've been keeping up with me, you saw me derive the speed of light from the wave equations of electrical and magnetic waves. You know, I'm sure I remember you being in there for that one as well, Lisa. So you know that speed of light is fundamental with respect to the movement of waves and the basically the constants, the vacuum constants specifically, not the waves themselves, but the electric and magnetic constants that limit how waves can move through space, determines the speed of light. So it stands to reason that since that is a universal constant, it would have something to do with everything else. But what he said was that, for instance, in particle accelerators, when particles are smashed together, and let's say they, have a clump of particles, and they know exactly what they are because they put them in the machine to accelerate them, and then when they clash together, they can actually see what's left. So they clash these things together, and they see this left, and they can see the energy that that was dispersed from that, or measure that energy, and it adds up to it conforms to this value. So experimentally, from particle physics as well as other things. That's the one that stuck out. But you mentioned like two or three things, that ways that we know experimentally that this is not just randomly just putting the speed of light there, but is actually precise, which I think is quite interesting. And it also brings up something else. Like I know from my modern lab that we can actually make electrons from high energy gamma photons, which is why I was able to get gamma rays off of scintillation from bombarding that crystal with radiation. And the energy that we get, if I remember right, is 500 uh, mega electron volts, 0.511 mega electron volts. This is the energy that we get split into so many units depending on the angle at which we hit it. Like if I hit the scintillation at a certain angle, then I'll end up getting half of that in this direction and half in this direction. But if I hit it at a different angle, I'll end up getting a third of it in three directions. So it always goes in um, uniform directions to conserve momentum, right? So the fact that we can make matter out of light, out of photons, because an electron is, I would say, is a piece of matter. I think that's quite interesting. So that seems to lend to the idea of how this is a valid and consistent thing that is just a remarkable fact of nature. Because at least in a small sense, I guess to a certain extent you could scale that up, but I'm not aware of us actually making a proton. Maybe that's possible, but I know in the early, at least the understanding is in the early universe, things were so hot and compact that things were just cramming together so fast that this process that we can see where we annihilate an electron, the reverse of that, or we can, ram high gamma rays together and make an electron. This process was happening on mass, and then we have all the matter that we have in the universe because it was just so hot and close together. Moreover, space and time, which Newton thought of as two separate entities, form a four-dimensional space-time. A more accurate summary of Einstein's viewpoint, therefore, is that the presence of mass energy causes space-time to be curved. We now have a third way of thinking about the motion of the teddy bear. No forces are acting on the bear, it is simply a geodesic in curved space-time. So the geodesic would be the straight line within the curved space. The professor talked about that on Thursday. If you take 2 points in an n-dimensional space or space-time, a geodesic is defined as the locally shortest path between them, right? So geodesic, locally shortest path. I guess it's not accurate to say a straight line in curved space, but I mean, if we think of the shortest distance between two paths, I guess in my mind, I think in curved space is this because space is curved, the shortest distance is a curve as well. So I guess that means that, and it does make sense. 'Cause like if we're on Earth, we know that satellites orbit the Earth, of course, in a circular orbit like this. And we also know that if we were to boost the satellite up high, it would actually take a longer time. It would go up, it would slow down, then it would speed up. So it does take a lot longer to go in the top path than the bottom path. And if we went this way, well, it'd just crash into the Earth. It wouldn't be able to keep going. So anything off of the geodesic either takes longer or doesn't take because it can't go. My understanding is yes, it's still not non-Euclidean. My understanding is Euclidean space specifically refers to space that we would consider to be flat. So they had mentioned uh, in 3.1, it says Euclidean space is also referred to as flat space. In this context, flat does not mean two-dimensional like a piece of paper. You can also have three-dimensional flat space. And here's the key. It says in Euclidean space, the shortest distance between 2 points is a straight line. The angles at the vertices of a triangle sum to pi radians. The circumference of a circle is 2 pi and so forth. So Euclidean space has to necessarily be flat. And in all cases, the three angles inside this triangle has to be 180 degrees. So basically alpha, beta, and gamma has to equal 180 degrees in order for it to be Euclidean space. That's Euclidean. So the surface of the Earth, for instance, would be non-Euclidean because a triangle is going to be more than that because the surface of the Earth makes it goes like that. And I tried to get this answer out of my cosmology professor, but he kind of said it would just take too long to go over it in class. He gave me some short answer, but it wasn't. But I was asking him how we measure. You know what? I asked my relativity professor too. I asked him how do we measure the curvature of space, and what he did was he picked up an eraser or something and dropped it. He said, "That's how." This is what he got. I like him. He's very amusing. Um, but I asked him, "Well, what about like foreign space?" Well, actually, that kind of answered my question. I think I asked my cosmology professor about foreign space because talking about cosmology stuff and deep in the universe. But my professor was basically saying, well, that's him. He's a cool guy. Like this is my second time taking a class with him. Like it's technically my third time. The first time I dropped it because I didn't really have enough time in my semester. Then I retook classical dynamics with him. That was last semester, and now I'm taking relativity with him. Um, Another demonstration he did was climb up on a chair and jump off, which I was worried about because he's actually a pretty old man. Like I was scared he was going to hurt himself, but you know he gets active in class. But I took his explanation to say though, when he took the thing and dropped it, that we know that there's curvature of space because matter is bending, is curving, like it's being pulled towards the Earth. So technically, if we was in flat space and we let go of the eraser, it should just stay there. It's like how we're in outer, or we're in free fall, right? Like if you're in free fall in the ISS and you let something go, it just floats there because because of the fact that you're falling. And I forget the way he worded it, but he worded it in some way when you're in free fall. I made a note of it. I don't remember. It's like you're temporarily experiencing Euclidean space when you're in free fall. and thus you experience weightlessness. And Lisa says having a professor that is passionate about their subject makes the best in class. Yeah, he's pretty cool. He's supposed to be. Uh, I know right now he does gravitational physics because it says it on his door. Like when you go to his office hours, he's like in the gravitational physics department. But apparently in the past he focused on relativity. But now, of course, gravity is the big thing because LIGO found gravitational waves and stuff. But also, so yes, Euclidean space is necessarily flat. If it's curved, it's non-Euclidean. So space, like for instance, the space here would have to be non-Euclidean because light is being curved through that space. But I'm still wonder, you know what? And I asked my TA from my cosmology class about deep space as well, and he said something to the effect that he understands from his research so far that even in deep space, like if you're in deep space and nothing is around, the understanding is that there is a slight curvature to space, even if you're not around uh, anything. But apparently the curvature is so slight that even calculating the radius of the curvature, we haven't been able to do like it'll take too much computer power to calculate the radius of the curvature because it's so slight. But he didn't know how they measured it either. Gravity. And they say per uh, if you take 2 points in n-dimensional space or space-time, a geodesic is defined as its locally shortest path. I have to remember that definition. Now we now have two ways of describing how gravity works. Oh, this is the part right here, what I was telling you about, by the way. Maybe I'll take a picture of it so you can see it. Hold up. Oh, 'cause I think this is important enough for y'all to see the actual wording since I was butchering the wording earlier. Hold on, let me take a picture of this real fast. Hey, all right, there we go. You'll be able to see what the words of the textbook says about this particular uh, thing. I thought it's pretty cool. I guess this is where I saw it. I guess maybe I was scrolling through the book. I know I saw it somewhere, and I might have just noticed that this was highlighted out and read it real fast. So the way of Newton, mass tells gravity how to exert a force. F equals negative g mm over r squared, and we did that yesterday. Force tells mass how to accelerate, right? And the general way of Einstein, mass tells space-time, mass energy, because we know E equals mc squared tells space-time how to curve, and curved space-time tells mass energy how to move. And Lisa says, I'm still wondering why our solar system still orbits the galactic center when the curvature of space is so slight. Dark matter? Um, well, put it like this. Um, I think the geodesic, the shortest path just is what it is. So however slight the curvature is, that's just the straightest line. Or maybe I'm misunderstanding the question. I think what you were saying, because I just realized I was talking about the solar system. So my understanding is this. So let's look at something small and work up. So we look at the Earth, right? We have ISS going around the Earth. Now, the ISS has many different particles, right? But all of them are in the gravitational field of the Earth. So everything is going to fall at the same pace. So therefore, if I was to zoom into this ISS, you have like a wrench floating in the air, and then you have an astronaut there. You have an ink pen there, and a blob of water, and them and the ISS are all going at the same pace. Because just like when we derived this equation here back in the day, even though I keep forgetting where I put it up in here. Here, maybe I'll highlight it green so I can find it more easily. Because when we derive this equation and we utilize the fact that uh, there's an equivalence between mi and mg, so we have F equals ma and F equals G M. Now I'll put M Earth M over R squared. So when we relate these two accelerations, at least these two forces over R squared, that's why that can cancel. And then we're left with this because the mass, the inertial mass, and the gravitational mass are the same. They're equivalent, so they cancel out. So all things fall at the same pace. And we get that on the Earth. Now, a few weeks ago, Lisa, we also did the thing where we calculated the gravitational potential, right? And we found that when you look at the Earth and you look at a certain radius from the Earth, there's a certain gravitational potential, and that gravitational potential determines that anything in this radius is going to fall at a certain speed or accelerate at a certain rate. And we saw that that matched the speed of the Earth, calculating it manually. We saw that that matched. The same thing is happening. And again, we have the planet Earth, we have us jumping up and down, we have boats and satellites and planes. Everything is basically in that same position, so we all fall at the same pace around the sun. Now, if we look at the galaxy, the same thing is happening. We can do the same calculation, which maybe I'll even do one week. It should be fun. So we have the galaxy, and the galaxy has a certain gravitational potential, and a certain radius from the center of the galaxy will also have its own gravitational potential. And we could do the same thing and solve for that, and we'll find that something that's certain distances away, because of that gravitational potential, will fall at a certain pace. And this will include because the gravity is so huge, just like how the ISS includes the people, the tools, the droplets of water, they're all going around the Earth at the same pace. This little point here would include the sun, the Earth, all the planets, you know, all of this stuff was all falling at the same pace. So the same dynamic works at all scales. And that's why this book was saying that when you get to larger scales, gravity is the dominant force, because on large scales, electricity, electrostatics cancels out. Everything, the universe is basically electrically neutral. The magnetic fields are so weak and they cancel out, and so on and so forth, that gravity is the determiner, and thus the gravitational potential is the determiner. And thus, all you have to do is just get the amount of mass within your radius and calculate the gravitational potential, and it'll output that everything that's in this distance away from the center of the galaxy will fall at the same pace, and thus we all orbit around the galaxy. Does that make sense, Lisa? It's just it can be calculate the gravitational potential of the solar system to the galactic center. Has that been done? I don't remember seeing it. Oh yeah, yep. But yeah. So I'm sure we can. I don't know if it's been done. Um, it should be complicated to do because we would have to get the math of everything. Ironically, though, and I don't even know how long do we take to go around the universe? I mean, not the universe, the galaxy. Is it like like 250,000 years? But we should be able to do the reverse as well. Just like how the orbit of the Earth around the sun uh, was consistent, right? And I'll make the sun the sun. Just like how the orbit of the Earth around the sun was consistent between just manually calculating the distance and the time and the gravitational potential. If we know how long we take to go around the galaxy, which I know we do, I just don't remember it off the top of my head, we could actually use that to reverse engineer the gravitational potential and find out what that is. Then we should be able to use that to reverse engineer the weight of the galaxy, which not necessarily would be the whole galaxy, but at least the weight of the mass that's within our radial distance from the center of the galaxy. So yeah, maybe I'll do that. Maybe that's something good to do next week. Oh my gosh, 230 million years? Damn, why was I thinking 250,000? What was I thinking about? I don't know what I was thinking about. Wow. I mean, that's understandable. The galaxy is so big. But now I'll be thinking, what in the world was I thinking about? You know what I was thinking about? Maybe I was thinking about the precession of the Earth, because the Earth the Earth's orbit precesses. Maybe that's every 250,000 years, like the actual angle of our North Pole precesses, like every 250,000 years. Hey, what's going on, MC Tune? How you doing? Thanks for dropping in. Good to see you. Yes, getting away from the dirt, doing some actual science discussion. Getting through one of my chapters from my cosmology class textbook. Yes, that's awesome, man. Good to see you. I was just talking with MC Tune to see if I could come on this channel soon to talk about my Persephone research. So that's been going pretty well. So I'm turning in my abstract tomorrow and be giving the presentation in March. So by that time, I should have everything worked out in great detail. We'll see how that goes. But awesome, yes. So Lisa gives us a good thing to do in one of the future weeks, looking at the uh, gravitational potential of the galaxy, determined from our position of orbit around the galaxy, just like how we did with the position of orbit of the Earth around the Sun, and we saw that was consistent. So the fact that we can do it with the Earth tells me to be consistent with the galaxy as well. Awesome. And we was just reading our Einstein Newton quote. So that's something good to keep in mind. We have Newton, mass tells gravity how to exert a force, force tells mass how to accelerate, mass energy tells space-time how to curve, and curved space-time tells mass how to move. So those are the two different ways of looking at the acceleration of mass. And there's Newton's way is good in a local sense, and relativity is when you have a whole lot of curvature of space, like a lot of mass going on. Lisa says, I would love to see that be a nice change of pace for the normal dirt flips. I agree. They get triggered in more debates. I actually think that'll be a good place for me, by the way, in this discussion. Being the person that goes to different channels and actually talks about science stuff. I was thinking about contacting FTFU as well as the founder of the experiment, Will Duffy. And maybe that'll be a good break on all these channels. Yeah, thanks for mentioning that as well. At least I was thinking the same thing. It's good to know that the idea is welcome. And maybe I'll contact some other channels as well, give more people other things to think about. Uh, Even though I know a lot of people like their dirt fix, but some people like a brick once in a while as well. So last few pages, and I actually hate geodesics. Remember it from my astrophysics class. I got through it. Thankfully, most of that class was writing a paper. I have 10 more pages left. Let's see if we can get through this. There's gonna be some math. Einstein's description of gravity gives a natural explanation for the equivalence principle. In the Newtonian description of gravity, the equality of the gravitational mass and inertial mass is a remarkable coincidence. However, in Einstein's theory of general relativity, curvature is a property of space-time itself. It then follows automatically that the gravitational acceleration of an object should be independent of mass and composition. It's just following a geodesic, which is just dictated by the geometry of space-time. Interesting. So basically, Newton, he was dropping a whole bunch of stuff, and he saw that because he was dropping, you know, he might not have dropped a feather because the air would have interrupted it. But all the stuff he did drop, he found that everything fell at the same pace. And thus, from that, we can conclude that inertial mass is the same as gravitational mass. And I guess it sort of happened to be a coincidence, but Einstein's way overlooks that entirely, or can ignore that entirely, and just point out the fact that, uh, as you said here, mass energy tells space-time how to curve, and curved space-time tells mass energy how to move, and thus, since space itself is curved, space-time that is, every single object is in space-time. So if you're in the same curvature of space, then space-time will be curved a certain way, and everything will fall at the same pace. So it's pretty cool. And this tune says trying to finish the wall in the office. Ah, awesome. Every time I organize, I lose everything. So usually when I organize, I can't find something because I put it somewhere nice and neat. Lisa says PhD Tony's debates are a mini course in themselves. Always learn something. Yeah, PhD Tony does always pretty good. He always gives what MC Tunes calls FE, or what is it, a free education? But the first never seem to learn. And you have a cool wall, by the way, MC Tune. You're talking about the wall that we see in the background, right? That has like the map and stuff on there. As long as you keep the map there, keep the map. The map is cool. I like how you point that out to the first sometimes. Lisa said we had a bad storm. Even the National Guard was called, and my driveway was full of mud. Spent all day digging it out yesterday. Damn. Awesome. MC Tune says he'll keep the map. It's good. It's always a good thing to point out when they try to say maps are flat. Like based on a flat earth, you mean. Well, glad you was able to get that worked out, Lisa. So thankfully I live in a dorm, so there's very little I have to do with stuff like that. I guess I call the maintenance people, like they have to come fix the zinc like one time. Describing curvature. So I think this speaks towards what you were talking about. And we covered a little bit of it actually. And this is called describing curvature, the next section. Right. So now we get into the part that, I mean, of course, I'm learning all of this stuff, but I remember from astrophysics that this could be a bit complicated. So let's see what we got. In developing his theory of general relativity, Einstein faced multiple challenges. Ultimately, he wanted a mathematical formula called a field equation that relates the curvature of space-time to its mass energy density, similar to the way in which Poisson's equation relates the gravitational potential of a space to its mass density. So we looked at the Poisson equation yesterday. En route to this ultimate goal, however, Einstein needed a way to mathematically describe curvature. Since picturing the curvature of a four-dimensional spacetime is difficult, let's start by considering ways of describing the curvature of two-dimensional spaces and then extend what we have learned to higher dimensions. The simplest of two-dimensional spaces is a plane, and illustrated in figure 3.4, for which Euclidean geometry holds true. On a plane, a geodesic is a straight line. Triangle is 180 degrees. I'll breeze through a little bit of this. We discussed this a moment ago. On a plane, we can set up a Cartesian coordinate system and assign each point a coordinate. On the plane, the Pythagorean theorem holds. So the distance between 2 points, so I have a point there and a point there, and have my plane yx, and so we have dl squared equals dx squared plus a dy squared. And he's calling dl the distance between 2 points in xy, and the distance is x plus dx, y plus a dy. We get into some of the basically what they're doing is they're putting this in what do you call it, differential form. So this will be dx, little change in x. Well, let's see if I can get the notations for this. I will say change in x equals x plus dx, and change in y equals x plus dy. And we're dealing with a vector. So with vector notation, uh, you can see the resultant equals x plus y. So I think that's what they're saying though. Now this is the distance between these 2 points. This is, let's say, x1, y1, This is x2, y2. So changing the L will be uh, x2 minus x1 and y2 minus y1. That should give us a distance between those two. And it seems like they're saying that this will be x and this will be x2. This will be dx. So we can say this will be x2 is x1 plus dx. So x1 plus dx minus x1, y1 plus dx minus y1. So we have dx, dy. And this seems to be what the book has. Oh, dx. I'm still tripped up on how to get in the addition between the two. I hate I hate some of the notation that's like this. Like I know we have a vector. Uh, keep wanting to put it in the form of adding vectors. Like if we're adding these vectors, then it'll be out like this. It's not the same as distance. So this would be the x plus y. The distance between the two. I have to think about the notation. So I should say the notation that they have is dl squared plus equals dx squared plus dy squared. But I have to think about how to get to the exact notation. Lisa says that her back is killing her from the lifting of the at least cleaning out the mud from the driveway. So it was nice when you was finished though. Job well done. Stating that equation 3.23 holds true everywhere in two-dimensional space is equivalent to saying that the space is a plane. Of course, other coordinate systems can be used in place of Cartesian coordinates. For instance, in polar coordinates, the distance between points would be dl squared equals dr squared plus r squared d theta squared. Awesome. Since it was hating gravity then, guess all we had to do was put the Earth in free fall, and then the mud would have been extremely light, and we could bring it back. Somehow stop it from falling again afterwards. Well, I guess technically it is falling, but we're just falling with it. Kind of interesting. All the equations 3.23 and 3.24 are different in appearance. They both represent the same flat geometry, as you can verify by making a simple coordinate substitution: x equals r cosine theta and y equals r sine theta. Now consider another simple two-dimensional space, the surface of a sphere. On the surface of a sphere, a geodesic is a portion of a great circle that is a circle whose center corresponds to the center of the sphere. If a triangle is constructed on the surface of a sphere by connecting the 3 points with geodesics, the angle at its vertices, A, alpha, beta, and gamma, obey this relation. Something to think like scientists for real, because we literally just drew this. Like exactly what the drawing that they have here is literally this right here. And they also use alpha, beta, and gamma. So it's good. Matter of fact, it reminds me like yesterday. When I say yesterday, I'm thinking like the last day in class. Institute says flat geometry, welcome to flat Earth. That's probably what they're actually saying too. That's actually how they think. And thermodynamics class, the professor gave us a sample problem. He said he had 4 coins, and he said he wanted us to construct a macro state and a micro state out of the 4 coins and let us know what multiplicity it had. And I picked a macro state of 2 heads up, and I calculated the multiplicity. If I remember right, it was 6, and it was four choose 2. And when he went to the next slide after everybody had enough time to put in their answer into the poll, this was the exact same example he had. And he asked who wants to answer, and nobody was saying anything. So I raised my hand and I answered. And then he changed to the next slide and said, "That's right." And he said, "That's exactly the example I had." And when he showed this example, it's exactly what I had wrote down. It was pretty cool. It was good enough so to think like scientists. So the scientists were using this example uh, here with alpha, beta, gamma, and it's pointing out that this would be more than 180 degrees if the space is not flat, at least if you're on the outside surface of a sphere. And it says the relationship it'll have in non-Euclidean space on the surface of a sphere is A plus, these alpha plus beta plus gamma would equal pi plus area divided by radius squared. And this is the equation I needed when I was starting on the homework. I went to the TA's office hours and I was just like, the homework had just came out. I was like, well, it just came out. I didn't have a chance to read the session yet, but uh, just was talking about several problems. He was letting me know I can solve that one particular problem with an equation in the book, and this is what it'll be. And this says, just looked it up. The max internal angles of a triangle and a sphere can be up to 3 pi. Yep, it's something like that. I remember seeing something like that in one of the questions or something. And the TA told me because I asked him, I mean, it seems to me, initially it did at least, that if you have a sphere and you draw a triangle on it and you keep increasing the size of the triangle, eventually you'll be on the other side of the sphere and the triangle will be getting smaller. But he said, no, what will end up happening is eventually the points of the triangle will touch on the other side, and that point determines the maximum size the triangle can get. So that must be at the point when you get to 3 pi, Lisa. So I thought that was pretty cool. Well, A is the area of the triangle. Going back to this equation here, A is the area of the triangle, R is the radius of the sphere. So A triangle and R sphere. This is equation 3.25. All spaces in which A plus B plus gamma is greater than pi are called positively curved spaces. Going back to what you were saying before, Lisa, how it's non-Euclidean. It has a curvature that is both homogeneous and isotropic. That is, no matter where you draw a triangle on the surface of a sphere or how you orient that triangle, it must always satisfy equation 3.25. So that's good to know. Right? With the radius r being the same everywhere in all directions, that's why it's homogeneous and isotropic. For brevity, we can describe a space where the curvature is homogeneous and isotropic as having uniform curvature. Thus, the surface of a sphere can be described as a two-dimensional space with uniform positive curvature. On the surface of a sphere, we can set up a polar coordinate system by picking a pair of antipodal points to be the north and south pole, and by picking a geodesic from the north to the south pole to be the prime meridian. If r is the distance from the north pole and theta is the azimuthal angle measured relative to the prime meridian, then the distance dl between a point r theta and another nearby point r plus dr theta plus d theta is given by this relation. You know what I'm saying? They get complicated with the equations now. Let's write this out. So they're saying we have a sphere. We pick the north and south pole with a prime meridian going between these two. R is a distance from the north pole. So if I pick a point here, this distance will be r. Theta is the azimuthal angle measured relative to the prime meridian. So it seems like they're saying theta is this. If I have that wrong, somebody let me know who's watching. I think they're saying that's theta, the azimuthal angle relative to the prime meridian. Then the distance dl between a point r theta and another nearby point is given by the relation dl squared equals dr squared plus r squared sine squared r over big R. So that's little r over big R for the two r's there. And move this down a little bit, times d theta squared. Now we're starting to get towards these metric equations. My astrophysics professor really liked metric equations, probably as much as I hated metric equations. But I learned it well enough to get through the class. So probably I'm going to have to revisit it for my cosmology class. I'll see why my research is in stars. To where I'm pretty sure after a while I'll get good at this too. Note that the surface of a sphere has a finite area equal to 4 pi r squared, and the maximum possible distance between points. In a non-Euclidean space, the distance between two points is defined as the length of the geodesic connecting them. The distance between antipodal points at the maximum possible separation is L max equals pi r. And that makes sense because the angle between these 2 points would be pi if you're dealing with a circle, and the circumference of a circle is 2 pi r, and the arc length is theta r. So that means that the longest distance between 2 points on the sphere will be the length of the prime meridian, where theta is pi, because it's half of the circle. So the longest distance between any 2 points on the sphere will be pi r. Does that make sense? I'll say L max. Yep, pi r. Lisa's on it. By contrast, a plane has infinite area and has no upper limit on the possible distance between points. That's another interesting way to demonstrate the globe, by the way. Just keep going in two directions, two different directions, and see if you meet up. Even though I don't want to be the one to pay for that. Doesn't want to cost too much. You have to just like make an unusual flight plan between two planes, and you could do it. I think we have planes that can go around the Earth. They can't do 1D. We know they can't do 3D. In addition to flat spaces and positively curved spaces, there exist negatively curved spaces. An example of a negatively curved two-dimensional space is the hyperboloid or saddle shape. And it drew the shape like this. So we have a saddle type thing. The inside is bending down, and we're coming down like this. And this is going underneath. This is curved as well underneath. And we're drawing a triangle. So just imagine that this is curving down, like you're literally have a saddle that you're about to put on a horse. This is curving up. And if we draw a triangle on this shape that's curving inward, it would actually have a negative curvature. So this will be alpha, this will be beta, this will be gamma. And obviously that would have to mean that alpha, beta, and gamma is less than pi. We'll see what they say. For illustrative purposes, it will be useful to show you a surface of uniform negative curvature, just as the surface of a sphere has uniform positive curvature. Unfortunately, the mathematician David Hilbert proved that a two-dimensional surface of uniform negative curvature cannot be constructed in the three-dimensional Euclidean space. Hmm. The saddle shape illustrated is in figure 3.6, and this is figure 3.6, has uniform curvature only in the central region near the seat of the saddle. Despite the difficulty In visualizing a surface of uniform negative curvature, its properties can be written down easily. Considering a two-dimensional surface of uniform negative curvature at radius of curvature r, if the triangle is constructed on the surface by connecting 3 points with geodesics, the angles at its vertices, alpha, beta, gamma, obey this relation. So this is the equivalent equation to the one we did before for the negative space. It's going to be alpha plus beta plus gamma equals pi minus a over r squared. This is equation 3.27. And I'll get a sip of water on that. Hey, what's going on, real kindness? Good to see you. Getting some cosmology in, specifically some geodesics, non-Euclidean space, and I'm already dreading it. The PSD from my astrophysics class is kicking in. Some metrics, the bane of my nightmares. We'll get through it. Should be easier this time. Let's see. And we have about what? About 5 more pages, 6 more pages, and we'll be through with this section. Where A is the area of the triangle, R is the radius of the sphere, or the radius of curvature, that is. I guess not the radius of curvature, but I mean radius of the sphere, but I guess technically we was able to draw a center here. This R, I guess it'll be basically a circle on the outside, like a mock circle on the outside. Uh, that R will be the radius of curvature. That's the R that we're working with in this one. Oh yeah, I started early because I knew I'd be going long. I knew I want to finish the rest of this chapter. Then I could finally start this cosmology homework. So yeah, but it'll be there to watch. Good guy to say flat cosmology. Well, it is flat enough to them. You know, flat earthers, they'll pull anything. Like, see, he drew a shape that's flat. He told you it's flat. I told you they believe it's flat. On the surface of uniform negative curvature, we can set up polar coordinates as well by choosing a point as the pole and some geodesic leading away from the pole as the prime meridian. I don't even know if I want to try to draw that one. I guess they're saying that this would be the prime meridian. If I could just pick any one, choosing some point as the pole, so I can choose that as the pole. If r is the distance from the pole and theta is the azimuthal angle measured relative to the prime meridian, so I imagine again they mean that this is theta. Distance dl between the point r theta and the nearby point. So basically we have point r theta and we have point r plus dr theta plus d theta. So they're saying dl squared for this on a negatively curved space is dr squared plus r squared. What is this called? Hyperbolic sine squared. R over r d theta squared. So this is the distance between 2 points in geodesic in a non-Euclidean space, where the geodesic is along a negatively curved space, and you want the distance between 2 points along that space. All right. So let's see where we go to next. Relations like those presented in equation 3.24, 26, and 28. By the way, this is 3.28. This was 3.26. And just like I didn't write down on 3.24. Oh, no, I did. It's right here. This is 3.24. So it's saying the relationships presented here between these distances in these curved spaces the general distance dl between two nearby points in space are known as metrics. So it was doing metrics already. In general, curvature is a local property. A rubber tablecloth can be badly rumpled at the end of the table and smooth at the other end. A bagel or other toroid is negatively curved on part of its surface and positively curved on other parts. And he says you can test this by drawing a triangle on a bagel. I don't know if I'll try that one. However, if you want a two-dimensional space to be homogeneous and isotropic, only three possibilities can fit the bill. The space can be uniformly flat, can have positive uniform curvature, or negative uniform curvature. Thus, if a two-dimensional space has curvature that is homogeneous and isotropic, its geometry can be specified by two quantities, kappa and r. So a two-dimensional space with curvature that is homogeneous and isotropic, the quantities it can have are kappa and r, where kappa is called the curvature constant. So the curvature constant, so K, kappa, equals 0 for flat space, kappa equals +1 for positive curved space, like the sphere, and kappa, you guessed it, is -1 for negative curved space, like the shadow that I drew earlier. At least I said I'm still pushing for the donut bagel shaped Earth because it's tastier. Hey, maybe just for that benefit, uh, if I get a marker for a bagel one day, just draw it small enough where I can still eat it. All right. And it says that if space is curved, then the quantity r, which has dimensions of length, is the radius of curvature. The results for two-dimensional space can be extended straightforwardly to three dimensions. A three-dimensional space, if its curvature is homogeneous and isotropic, must be flat or have uniform positive curvature or uniform negative curvature. Interesting. So the reason why uh, three-dimensional space, and by the way, I actually thought about this one because I had asked my cosmology professor about the curved space in distance. And like I said, he didn't give a full answer because he said it was kind of too much of a departure from the topic at the time. They gave me a small answer that made me consider it, gave me enough to consider it. So in cosmology, like we spoke about yesterday, we're looking at um, squads of the universe that are 100 megaparsecs or bigger. And if we look at a small enough space, we can see that the universe is non-uniform. Like, we look at the solar system, there's the sun, and that's very different from anywhere else in the solar system. But if you zoom out far enough, we find that matter all looks the same. Like at a big enough scale, galaxies all form these superclusters. And matter of fact, it's the cover of the book. Thinking about it, let me increase the cover of the book really fast. This is what I'm talking about right here. So I know this looks like a neuron or something like that, but these are actually the megastructures that that we can see in the larger, you know, view of the universe. And the reason why we know it's like that, by the way, is because when hydrogen suffuses almost everything. Hydrogen is the yeah. Hydrogen suffuses the universe at large. We know hydrogen is the most abundant universe element in the universe. It's like 75% of all matter in the whole universe is hydrogen. We know stars are mostly hydrogen. And there are these big clouds of hydrogen everywhere in the universe. We call it the intergalactic medium. So what happens is uh, when light is going through the universe and it hits one of these clouds, so much of it is going to be absorbed, and then so much of it made it through, and then it hits another cloud, right? And so much of it is absorbed, and what they can do is they can study the light, and they also know that as we look farther into the universe, light has a redshift, and the redshift happens at a certain frequency where there's a cutoff, where basically um, there's a certain frequency of light that hydrogen just completely absorbs. They call it the like there's a cutoff point that I believe they call the Lyman alpha forest, where beyond that point, hydrogen just absorbs all the light. So only the light that's above a certain frequency can we see. So combining this with redshift, we know that if, for instance, we get only this amount of light from this galaxy, and this amount of light has this redshift, Z equals whatever, then we know that at this point of the galaxy, there's a certain amount of density of it there. But at the same time, let's say there's another part of the galaxy where there's not as much gas. And let's say we get this much light from there and it has this redshift. Well, then we know that the area is mostly clear here. And let's say we get some light from some distant galaxy here and we don't have much of a cutoff. We know it didn't hit a lot of hydrogen. And this light has this redshift. So basically, they painstakingly went through light through several regions. And in this way, they basically came to the depth of the universe. And then we end up getting something like what's in this image here. Oh, and y'all was not seeing what I was writing there. That's what I was writing. Let me move this image to the side. So basically, this is the first thing I was writing. Light got captured a whole lot, and we got a little bit of it. And we see the Z from here, so we know that there's a wall there. And this light came from there, and we got this much of it. And it has this red shift. And this light didn't hit anything, so we have this red shift. As you can see, by the amount of light that we get, by the red shift of the light, by what a cutoff is, we start to be able to paint a three-dimensional picture of the universe. So basically, they did this, and we was able to get this structure that we have where we can see that the universe is made this way or shaped this way. And maybe I'll put a crop on this thing so I can keep the image up. So I think it's a pretty cool image. It'll be a good visual as we continue to talk about these metrics, and maybe that topic will come up again. Boom. I'll make that. Boom. And boom. You So that's how we figured out that the universe is shaped like this. So therefore, going into the universe, I was saying all that to say that when we get a big enough view on the universe, everything looks the same. Therefore, since at a large enough scale the universe looks the same, we know that the average curvature of the universe must be consistent because the mass is generally distributed. And even this is not a very uniform view. Like you could actually see that there's a very big cluster of galaxies in the center right there. But when you zoom far enough out, like one of the pictures they showed in my astrophysics class, everything just looks very uniform. Tired, like, yeah, you said photos get tired when you travel too far. Ironically though, Lisa and real kindness, this is the thing. We actually point that out as a what do you call it? A stupid statement of flat earthers, and I mean technically it is because they don't know any better. They just I don't they just, but actually that was actually a big debate in the past. My cosmology professor went over that Thursday. He was saying how there was two competing models of the universe. One model of the universe was that it's static and more matter is being created. And the only way they could explain redshift is to say that light got tired, that light lost energy. And if I remember right in his slide, he even had that terminology, light got tired. So this was a theory that they were uh, trying to posit to promote a static universe. And the competing theory was the Big Bang theory, which at the time seemed like fanciful. And what he was saying was the term Big Bang came about because people were making fun of it. Like the static Earth people were saying, "Oh, they're saying it was a Big Bang," and it was they was making fun of it, right? But what happened is eventually we I'm sure there must have been some other things before that, but the main thing happened was when we observed the CMB, and we know that the CMB it has a perfect black body, so we know it was a black body emission. We can calculate the wavelength of it. Like right now, is a microwave wavelength from from measuring it. That's why we call it the CMB, the cosmic microwave background. But when we back calculate the temperature and energy of the CMB to the Big Bang time, it matches to a CMB, to our universe being as hot as we understand it to be, as long ago as we understand it to be. And it matches the redshift of a universe where light doesn't get tired. It goes, continuously in the vacuum. So ironically, they were legitimate scientists at a certain point, which actually thought that was true. But the CMB was one of the things that allowed us to throw that out. And now, of course, it's a disgrace. And now this flat earther said, but there was a period of time when we didn't understand light as well as we do today, and people thought that might be a real thing. At least it says Wiki from Trans. It's Wiki. Yeah, yeah, yeah. I wrote about his Wiki when I did those papers about dark matter and dark energy. He's pretty cool. He introduced me to the virial theorem, which actually we got introduced to again in one of my classes. It's something to blend together a bit. Thankfully, at these higher classes, some things overlap. Like in cosmology, we're talking about relativity. We have to because we're talking about these great distances and these large bodies. And of course, relativity, we're talking about relativity. And I believe in my thermodynamics class, we talked about relativity a bit as well. As you start to get into higher math, a lot of things have to be taken into account in higher physics. We were talking about the curvature of space. The result for two-dimensional space, it can be extended. So basically, we're extending the same thing we did in 2 dimensions to 3 dimensions. We have dl squared equals equals uh, dx squared plus dy squared plus dz squared. I'm still not clear on the notation change expressed in Cartesian. By the way, this is 3.29 in case I refer to it later. And we have in Cartesian or spherical, we have dr squared equals dr squared plus r squared d theta squared plus r squared sine squared theta, uh, and then d phi squared. And this is 3.30. If a three-dimensional space has uniform positive curvature, its metric is, all right, here we go. We have the distance between two things in a positively curved space, which will be our universe, dr squared, or at least our planet at least, r squared, sine squared, r over r. And they're multiplying all of this to d theta squared plus sine squared theta d phi squared. All right. So this is three-dimensional space with a uniform positive curvature that's kappa equals 1. This is equation 3.31. A positively curved three-dimensional space has finite volume, just as a positively curved two-dimensional space has finite area. That makes sense. Positively curved three-dimensional space has finite volume, which I'm still not clear about, by the way. Because, I mean, I imagine thinking about it now, like the universe expanded from a point, uh, all of the space now is this. So it seems like universe should have an edge. And that's when my TA said, well, there is a slight curvature to the space. It's so slight that we can't calculate the radius, but there is a slight curve. But at the same time, if this is space expanding, then technically space can only be within this, um, radius, whatever the radius is that causes a slight curvature of space. So it's still a conundrum to me. Like, what is it that's outside of the universe, or what was it that was outside the uh, you know, the singularity that later expanded to become the universe today? Guess we might never know that. A point at r equals pi r is the antipodal point to the origin, just as the south pole is the antipodal point to the north pole. That makes sense. If you have a point here, as we discussed earlier, a pi r distance would be there. By traveling a distance c to pi r, it is possible to circumnavigate a space in uniform positive curvature, like the planet, the surface of the planet. So that does work. So I guess this is just a more complicated way of doing what we did before, right? Because didn't we get a distance on the outside of a sphere? What was it? Yeah, that equation. Was it in the last section? We find through these sections, aren't we? Here it is. So I know we got something for. Oh, I got you. I'm sorry. This is for the angles of a triangle. That's what it was. So that's different. The angles of a triangle is that. But this is the actual distance between two points on the triangle. So that's a difference. I was mistaken that equation. Finally, if a three-dimensional space has uniform negative curvature, that's kappa equals -1. So in other words, this was kappa equals 0, flat space. This is kappa equals +1. And now we have kappa equals -1. All right, here we go. So we have dl squared equals dr squared plus r squared, hyperbolic sign squared, little r over big R. And that's all going to be times d theta squared plus sine squared theta d phi squared. So uh, that's 3.32. Like flat space, negatively curved space has infinite volume. Interesting. So positively curved space, if you go straight enough, you will hit an antipodal point and you'll get back to the point where you started if it's uniformly curved. Flat space, of course, you could just keep going. And negatively curved space is infinite. And of course, that makes me think about the inside of a sphere, but I guess they don't think about it that way. Three possible metrics for a homogeneous isotropic three-dimensional space can be written more compactly in this form. So this is a more compact form for three possible metrics in a homogeneous isotropic three-dimensional space. We have dl squared equals dr squared plus s kappa r squared, little r squared, and d omega squared. This says another nutty Earth model where, all right, I see. So all they did was just compact that part. D omega squared is defined as this. So this is d omega squared. So no need to write it again since I have it here. And this we just plug that there. And S kappa is going to be this S kappa of R. And that's why we have this here. So it looks like to simplify the writing of the equations, it is called R squared. Not even saying R squared, they're just saying R. But it seems like, oh, I see. So they square the whole thing. I forgot I didn't put my square on it. So actually, this is SKR squared. Okay, there we go. So the squared is not on the R, the squared is on the whole thing. R. But it's saying that this whole thing is SKR squared, which is this whole thing in this metric, and this whole thing here is d omega squared, which is d omega squared. So that's the shortcut for the notation. And it looks like the flat space is still going on. And I actually distributed this, not knowing it was going to make a shortcut of it later. I'll go ahead and change it and put it into the shortcut form. Well, now this is bracketed, and the same thing happens for this metric. R squared by itself is SK squared. And that's the wrong equation. Mm, is it? They're saying that SK is 0. I see. For flats for K equals 0. So we have R squared. Okay, I got you. So this is still that. And now in flat space, this will be our SK. This will be our SK. All right, there we go. So these are the different ways of writing these metrics in shortcut form. So it may come in handy later if they put it in shortcut form on the exam. And the limit of R is very much less than big R. So R would be the distance on the surface. Big R would be the radius of the, so R is the distance between a point, the R that goes to the distance between 2 points. Big R is the radius of curvature. So if the distance between 2 points on the surface here is very much smaller than the radial the distance of radius, then SK pretty much equals R regardless of the value of K. So you have you know what they're saying right there? They're saying that if the if the sphere is big enough, if the sphere is big enough such that the radius from the surface to the center is big R, but the distance you're taking across the surface is small enough, little r, it eventually, or it starts to approach the limit that SKR equals R, which means it measures flat on short distances, which is what I've heard several people say. This thing has been arguing for the longest time in those debates. If you're on the surface of a sphere, would you measure a small enough section of the sphere for a big enough sphere, it'll seem flat in very short distances. Even though I've seen people like take the horizon, but I guess that's to my point. They're actually taking a very wide view of the horizon and a shrink in the image. So I guess if you take a small enough section of the horizon, even like if you have just 2 pixels, I mean you just have 2 pixels, so it seems flat. So that says if you take a small enough cut of a sphere, uh, it'll seem flat if it's a small enough cut. Even though as r little r approaches r, becomes more and more, at least the bigger r, the less of a difference between r small and r big there is, the more the positively curved surface will be recognized as a positively curved surface. At least it says, which is why flips are always confused about everything, really. They want to be confused. All you have to do is just look at that talk I had with Flatzoid a month ago or whenever it was. And you see, I actually showed the image on the screen. I'm like, this is what we agreed to. We agreed that you were going to present why the second law of thermodynamics means we can have an atmosphere and I can challenge it. Stop asking me questions. Stop trying. Just present it. It's because he knew he couldn't. So he had to just say, "Oh, you don't understand. I'm going to leave." Right. Uh, so he still doubled down, like I showed you on the reviewing a little bit of his. Yeah, exactly. He admitted it. I showed that clip where he said I gave him the link, but the equation is not in the link, and I saw him scrolling trying to find it. Oh, it's not there. But like I said, he wants misunderstanding. They all do because I guess that's how they pretend that they know. They just cause confusion and pretend that means they know better. And flat earthers believe it. They fall for it. I mean, he still has 4,000 followers, so they believe it. Flat soil disrespect and critical think on FTFEs was a doozy. Yes, it's crazy, but that's another thing that made me not want to talk to these people anymore either. Like if a flat earther sees that and you still want to follow that guy, it's just I see no point in talking to you. None of them. It's like, dude, how can you see that and he still has 4,000 followers? It's just amazing. You should, but yeah, I think the last thing I saw was that uh uh what do you call it, larger mark thing? Because I've seen things he said before, and I thought he was a smart guy. Yeah, but I guess maybe he just found somebody who has something good to say to parrot. But he's been repeating the same flat earth nonsense as all the others. So that actually had my attention because I actually thought he was an intelligent guy, but apparently not. He's just a flirt like a derpy flirt like the others. But there we go. So we know as aura gets very much smaller than big aura, SK approximates R, which means on a sphere you measure a small enough section and measures flat. When space is flat or negatively curved, SK increases monotonically with R. Okay? Well, I can see it with P equals 0 because it's just R, right? But why with negative one? Think about it. SK goes to infinity as R goes to infinity. Okay, so I guess because the way they're describing negatively curved space, it never meets. It's not like the inside of a sphere where it connects; it just goes on forever, but it has a negative curvature. So therefore, it could just go to infinity. By contrast, when space is positively curved, it increases to a maximum of S max equals R at R over R equals pi over 2. So S max equals R at R divided by R equals pi over 2. So the maximum distance is going to be the antipodal distance, S max. Okay, so what's confusing about this is I'm forgetting that they're talking about this. It's saying SKR for positive space is R sine R over R. All right, so that makes sense when you keep that in mind because sine of pi over 2 is 1, and if R over R equals pi over 2, then that's going to maximize sine, and this is a sine. So that makes sense. You have to keep in mind the actual equation he's talking about. I was thinking about just that. I have to keep this shortcut in mind. So I'm glad I went over the shortcut because I would have forgot. I would have missed that. Then decreases again to 0 at r over r equals pi. Of course, because uh, sine of pi is 0, the antipodal point of the origin. Interesting. Okay, so that makes sense. The coordinate system r theta phi is not the only possible system. For instance, if we switch to radial coordinates from r to x, x is defined as skr or s capital R, then the metric is dl squared equals dx squared over 1 minus kx squared. And only this part is divided by r squared plus x squared d omega squared. And remember, the d omega squared is the shortcut for the whole second thing, and that's 3.36. And this 1, all right? Although metrics written in 3.36 and 3.33, and put a number by 3.33. This is 3.33. So although metrics written in the equations 3.33 and 3.36 appear different on the page, they represent the same homogeneous isotropic spaces. They merely have a different functional form because of the different choice of radial coordinates. It all looks ugly to me. Okay, last few sections. On the last few sections, then we'll call it the Robertson-Walker metric, 3.5 Robertson-Walker metric. So far, we've considered the metrics for simple two-dimensional and three-dimensional spaces. However, relativity teaches us that space, see what I'm saying? Relativity, cosmology, comes in hand with these large distances. Relativity teaches us that space and time together constitute a four-dimensional space-time, which I don't know if I covered this yesterday, but we have s squared equals ct squared plus x squared plus y squared plus z squared, something like that. Still learning relativity, so, but I'll put a question mark, but I believe that's what it is. Just as we can compute the distance between 2 points in space using the appropriate metric for that space, so we can compute four-dimensional separation using two events in space-time. Oh, I was close. Oh, they just use a different metric. That is it. So they have, oh, and I should put a D here. That's why I'll just keep it the same. Similar to this. So they have it as ds squared equals negative c squared dt squared. And they're using the spherical coordinates, dr squared plus r squared d omega squared. And this is 3.37. Instead of two events, one occurring at the space-time location tr theta phi, and another occurring at the space-time location just t plus dt, r plus dr, and so forth. This is the distance between those two events, all right? The given metric in the equation 3.37 is called the Minkowski metric, and the space-time that it describes is called Minkowski space-time. I've heard about Minkowski space. And Lisa says that first half scripts they regurgitate all the time, then the first reset kicks in if they were in it to learn anything. You're exactly right. And then a funny thing in that talk I had with Flatzor, he started with the same script. He was saying, "Oh, you only need the equation. You could just do the box and the whatchamacallit thing." So I asked him, "Okay, then use this logical equation to let us know about the cardinal efficiency of an average power plant." And then he immediately jumped to, "Oh, I have an equation. I have an equation." Well, hold up. Show us your logical thing. It's quite interesting to watch. I still do find the psychology of it interesting, but not interesting enough to keep going. MC Toon says, okay, wrapped up the work on the wall for the night, heading out. Hey, thanks for joining, MC Toon. Appreciate seeing you. Awesome seeing you in the comments. And we'll get that date set for the Percepia talk. Matter of fact, I was working on some of that coding earlier, so it's coming along pretty well. Hope you have a good evening. Photon's path through space-time is a four-dimensional geodesic, and not just any geodesic, mind you, but a special variety called a null geodesic. Okay? A null geodesic is one for which, along every infinitesimal segment of the photon's path, ds equals 0. Okay? This makes slight sense for my relativity class because if you have a light cone, the 45-degree angle is the angle of light going at the speed of light. so the distance it covers, like ct squared divided by x squared plus y squared plus z squared is 1. So the speed of light divided by the time it travels, this is c squared, is going to equal 1 for light. So I think that's how they get in this zero thing. That is how they get in the zero thing. Because if we look at the equation, ds squared equals negative c squared dt squared plus, and I'll just use the notation I'm familiar with first, x squared plus y squared plus z squared. This distance in spherical coordinates is also negative c squared dt squared plus dr squared plus r squared d omega squared. There's a minus here, so it's going to equal 0 because the amount of space light travels at the speed of light is going to be the amount of distance light travels at the speed of light. So these things are going to be equal, and then it's going to zero out, uh, and that's why that's the case. And that would explain why Minkowski has a 0 there. Oh, do you want me to repeat something, Lisa? I know this stuff is confusing to me as well. You're talking about Minkowski space. Yes, the C equals 1 trick, real kindness, which I sort of hate. But the good thing about this book, by the way, they mentioned it early on. They said, even though they mentioned the convenience, the convention of doing that, not only C, by the way, they make C equal 1, K equal 1, the Boltzmann constant, H bar equal 1, right? Planck's constant divided by 2 pi and the gravitational constant equal 1. They make all of those equal 1. But what he said was, even when he does make all of those equal 1, he'll still keep the units there, or he will actually keep the units there so we can actually see what's going on. But yes, apparently they do that. Um, but I asked my TA about that in my cosmology class, and he was saying that oh my gosh, what royal graph happened with, oh, I minimized something. That was my bad. There we go. Even though that happens, uh, uh, we can always put the units back later and get the same thing. But I still think it's kind of weird. Yeah, it is kind of complicated. Let me know what didn't come through. If you want me to clarify something, I can clarify it again. It is very complicated stuff. Just barely hanging on because I've seen a lot of it before. Even though I imagine in this class we're going to go in more detail about everything. If the photon is moving along a radial path, by the way, this is 3.38. If the photon is moving along a radial path toward or away from the origin, this means that since theta and phi are constant, there we go. So this is basically, so what they're saying is what I have here. So at least this part I get, but I have seen this concept a few times. So basically we know that, like with is this Pythagorean theorem? No, not quite. This is just, we know that if we have a vector, like if we have x, y, z, and we have a vector in this space, r, let's see, r vector, we know that we can get the magnitude of r by doing the square root of x squared plus y squared plus z squared. We know we can do that. So we can say that ds squared equals negative c squared dt squared. plus r squared, or I guess I should say dr squared. And we know with light that equals 0. So in Minkowski space, dt squared equals dr squared. And this is what they call equation 3.39. We go into a little bit more detail, see if it helps. And Real Cognitive said, Lisa, I highly recommend Lenny Susskind's continuing education courses on the Stanford channel, especially cosmology and general. And what is GE? Unless that was meant to be an aura. I know aura is right next to E. General relativity. I might have to look at that myself. Awesome. I have heard of these Susskind videos before. I think I even bookmarked them, but I never looked at them yet. Always meaning to watch a lot of videos, but I seem to never either have the time or make the time to watch them. The learning assistant for my Quantum 2 class gave us some videos to watch that I haven't watched yet. The Minkowski metric of equation 3.37, that equation here, applies only within the context of special relativity. With no gravity present, Minkowski spacetime is flat and static. When gravity is added, however, the permissible spacetimes are more interesting. In the 1930s, the physicists Howard Robertson and Arthur Walker asked, what form can the metric of spacetime assume if the universe is spatially homogeneous and isotropic all the time, and if distances are allowed to expand or contract as a function of time? The metric they derived independently of each other is called the Robertson-Walker metric. All right. So this is written. So this is basically the metric of an expanding space. We have ds squared equals negative c squared dt squared plus at squared. And in parentheses, we have dr squared plus skr squared times d omega squared. So this is all added up in the box there. So this is the Robert. Y'all see why I hate metrics, by the way. Y'all see the pain of metrics. This is the Robertson-Walker metric. So this is the metric that allows us to calculate the distance. And by the way, to give an overview, um, these metrics allow us to calculate distances. So I remember in my astrophysics class, he would give us coordinates, and we would have to utilize these metrics. Like he would give us coordinates in a certain space, and we have to utilize that metric to find out how much distance is between those 2 points. And it'll be different according to which metric you use, um, because the geodesic in different spaces have different curvatures. So we had to apply this thing that I remember the exact name of to get those distances. And we're coming down to the end, almost finished. One more section after this. So this is the next to last section, then we'll be done. So I'll go a little bit after 9, where the function skr is given by equation 3.53, where r equals r naught, and the spatial component of the Robertson metric consists of the spatial metric for a uniform curved space of radius r theta, this radius r naught, scaled by the square of the scale factor at, right? So basically what they're saying is this is sort of a repeat. This is 3.41. This is basically a repeat of the equation 3.35, which put a number by it. Either I didn't put a number. Oh, that's the SK. So it's saying we're still using, I didn't put a number by it, but technically this is 3.35. The fact that like everything in blue is 3.35, the SK thing. So basically we're keeping the same SK thing. Uh, R is R naught. I guess we could remove it because R is at the origin, or there is no space is expanding, so I guess there is no definite curvature to the space or definite radius because the space is expanding. And the spatial component of the Robertson-Walker metric consists of the spatial metric for a uniformly curved space of radius R naught. And they say compare it to equation 3.33. So basically it's similar to this equation, except now we have the speed of light up in there, the c squared up in there, dt squared. And at, this is the uh, factor by which the universe is expanding. So we have 2 points today. Tomorrow, after the universe expands, even though these 2 points didn't move, the expanding universe will have brought those points farther apart because space is expanding. And the term that determines how much this changes is called AT. That's what that AT term is. The scale factor, first introduced in section 2.3, describes how distances in a homogeneous isotropic universe expand or contract with time. We just covered that, but I know they was going to review it. The time variable t in the Robertson-Walker metric is the cosmological proper time, called the cosmic time for short. Hmm. So this t is cosmological proper time, and it's the time measured by an observer who sees the universe expanding uniformly around him or her, which is all of us. The spatial variables r, theta, and phi are called the co-moving coordinates of a point in space-time. If the expansion of the universe is perfectly homogeneous and isotropic, then the co-moving coordinates of any point of any point remain constant with time. So these co-moving coordinates don't change in the Robertson-Walker metric. In other words, if this is xy, this will still be xy, which I think is kind of odd. But I guess it's just, this could be 1, 2, and this can be 3, 4, but it's just the number of units between them. We would have to add a number of units, but we could still define that as 1, 2, and 3, 4, and everything related to these 2 points. If this is 5, 6, you'll still be able to find everything in the same distance relative to each other, but it's just the space between them will be bigger, but all the coordinates can be placed exactly the same. So that's what they're saying. As space expands, we should be able to use the Minkowski metric to still find locations, even though the distance between those points will change. The coordinates marking those points will stay the same because space is expanding the same amount in all directions. The assumption of homogeneity and isotropy is an extremely powerful one. If the universe is perfectly homogeneous, oh, I just covered that. Awesome. All right. We're going to the last section. Last section, proper distance. A lot of equations. I don't write them all down. Tell you what I'm going to do for this one. I'm going to take pictures of this one and show the book. So y'all can see my pain that I'm going to have on this homework. Y'all can see it. So give me a moment. Instead of just reading this and writing them down, I'll take pictures of this one and highlight the pictures. We'll see how this works. So give me a moment. I'll move my mic to the side. Fashion all funny. They put me on the screen big so I get these pages in the book. hold the page down. Pretty much two pages of this chapter. Give me a moment. Get these placed in. I should take a picture of a page I didn't need to take a picture of. I got an extra one there. Remove that one. Not perfect. Will do. Let's see what this looks like. I'll see if it's good enough. I could just read. Oh, see if it's good enough. I could just read the text here. Got the mic back. All right, here we go. Proper distance. Consider a galaxy far away from us, sufficiently far away that, oh, this does this sometimes. There we go. That we can ignore the small scale perturbation of space-time and adopt the Robinson-Walker metric. One question we may ask is exactly how far away is the galaxy? In an expanding universe, the distance between the 2 points is increasing with time. Thus, if we wanted to assign a spatial distance, we must specify the time t at which the distance is the correct one. That's crazy. Suppose that you are at the origin and that the galaxy that you're observing is at a co-moving coordinate position r theta phi, as illustrated in 3.7. The proper distance dp between the 2 points is equal to the length of the spatial geodesic between them when the scale factor is fixed at a value at. So that's why at was in the equation, because at has to let us know when we're looking at the distances, so we know that we basically assign, okay, at this time, the distance between those 2 points would be this, and we get the proper distance. A time later, because the universe is expanding, the distance will be this. Even though the coordinates are the same, the distance is different. And as you can see, these are the equations. Save y'all from seeing me write them all over. Write these down. The proper distance between an observer and galaxy can be found using the Robinson-Walker metric at a fixed time. This is this one. Along the spatial geodesic between the observer and the galaxy, the angle is constant because we have this. And the angle is constant because everything is expanding in the same, with the same distance between them. So again, this angle here, we call it alpha. It'll be the same alpha here, even though this distance r, I'll call this r prime and I call this r. R prime will equal not r, but the coordinates will be the same and the angle will be the same. The proper distance dp is found by integrating over the radial co-moving coordinates. That got a little dark there. Because the proper distance has the form dpt with the co-moving coordinate r constant with time and the rate of change for proper distance being between them, and the distant galaxy is this, right? And let me write this out since this is a bit dark. A dot r, so this is the change in that metric between the distance between different points, a dp, right? We have some more equations that are dimmer. Thus, at the current time t equals 0, there's a linear relationship between the proper distance to a galaxy and its precession speed. So this one is Vp t naught equals h naught dp t naught. Interesting. So since the Hubble constant tells us how much a galaxy is receding from us the farther away it is from us, that's linked to the fact that the farther away we see a galaxy, the farther in the past in time it is, and thus is linked to the AT term because that'll tell us uh, the change between locations in space that far away. Okay, well, kindness, thanks for letting me know. I should be here for probably another, what, these 2 pages, another 10 minutes, I guess. In a sense, this is just a repetition of what was demonstrated in section 2.3. The distance between points is proportional to AT. There will be a linear relation between the relative velocity of 2 points and the distance between them. Now, however, we're interpreting the change in distance between widely separated galaxies as being associated with the expansion of space. As the distance between galaxies increases, the radius of curvature of the universe, r equals AT, increases at the same time. That's what we were saying. It'll take so much to calculate the curvature in space because technically it's the curvature of the universe, at least where we're at. Like if we're here in the universe, then r will be, still seems to me there will be a center somewhere. But I know they say there's no center everywhere, it's a center. But to me, it seems like there'll be some point here where the origin of the curvature will be, which seems to suggest that at that point, I guess nothing will be at that point because this, yes, confusing. I guess only the very, very smallest things, like that are so small that they're virtually in the same spot as the point of expansion, would still be close enough to that point where they experience any reasonable curve. Some cosmology books contain a statement like, as space expands, it drags galaxies away from each other. Statements of this sort are somewhat misleading because they make galaxies appear to be entirely passive. On the other hand, a statement like, as galaxies move apart, it drags space along with them, will be equally misleading because it makes space appear to be entirely passive. As the theory of general relativity points out, space-time and mass energy are intimately linked. Yes, the curvature of space-time does tell mass energy how to move, but it's mass energy which tells space-time how to curve, which is what I was thinking about earlier, how on large scales the mass is uniform, so therefore we have a um, certain curvature of space overall. The linear velocity distance relation given in equation 3.46, which was this one I wrote here, seemed like this would be an important one, implies that points separated by proper distance greater than the Hubble distance will have a velocity greater than the speed of light moving away from us. So that's what this is saying. Things that are farther away from us than the Hubble distance will be moving away from us at greater than the speed of light. Using the observationally determined value of the Hubble constant, the current value of the Hubble distance in our universe is this. So anything farther away from us than this will seem to be moving away from us faster than the speed of light. That's 4,000 something megaparsecs. Thus, galaxies farther than 4,400 megaparsecs from us are currently moving away from us at speeds greater than that of light. Cosmological innocence sometimes claim, gosh, doesn't this violate the law that massive objects can't travel faster than the speed of light? Actually, it doesn't. The speed limit that states that massive objects must travel with v less than c relative to each other is one of the results of special relativity and refers to the relative motion of objects within a static space. In the context of general relativity, there is no objection to having 2 points moving away from each other at a superluminal speed due to the expansion of space. When we observe a distant galaxy, we know its angular position very well, but not its distance. That is, we can point in its direction, but we don't know its current proper distance. We can, however, measure the redshift of the light we receive from the galaxy. Although the redshift doesn't tell us the proper distance of the galaxy, it does tell us at what scale factor A was at the time the light from the galaxy was emitted. So in other words, when we see light from a galaxy, we're not seeing where it is now, we're seeing where it was when it emitted the light. To see the link between A and Z, consider the galaxy illustrated in the figure 3.7. So this is here. An observer at the origin observed the galaxy at coordinate position. A photon emitted by the galaxy at cosmic time t reaches the observer at cosmic time t naught. So it reaches us here, but it was sent there. We call our cosmic time t naught. I almost tried to scroll sideways like a book. During the travel from the distant galaxy to us, the light traveled along a node geodesic with ds equals 0. The node geodesic has theta and phi constant. That's along light's node geodesic. So apparently, light doesn't experience the expansion of space because it's traveling. The amount of space it covers is the same thing as the amount of time it takes. It seems like it doesn't experience the expansion of space because in every single point in space, its speed doesn't change. Rearranging this relation, we find c times dta equals dr. In equation 3.53, the left-hand side is a function only of t. The right-hand side is independent of t. Suppose a distant galaxy emits light at wavelength lambda as measured by an observer in the emitting galaxy. Fix your attention on the single wave crest of the emitted wave. The wave crest is emitted at time te and observed at time te such that, okay, the next wave crest of light is emitted at time te plus lambda over c, and is observed at time to plus lambda over c. That's because this is meters over meters per second, so that's seconds. Where in general, lambda equals not lambda for the second wave crest. Comparing equations 3.54 and 3.55, we find that these equations are equal. Interesting. So it's saying that these two things are equal. And you notice they both have a c, so the c cancels. That is, the integral of d over at between the time of emission and the time of observation is the same for every wave crest in the emitted light. If we subtract the integral, oh, this one got too dark to read on the book. I'll read this one for y'all. Let's scroll a few pages. Oh, by the way, we're on the next to last page. On the last few paragraphs, guys, and we'll end. So we're here. That is the integral of dt over at between the emission of successful wave crest is equal to the integral of dt over at between observations of the same two wave crests. This relation becomes still simpler when we realize that during the time between the emission and observation of two wave crests, the universe doesn't have time to expand by a significant amount. The time scale for expansion of the universe is the Hubble time, 14 gig years. The time between wave crests for visible light is lambda over c is about 2 times 10 to the negative 15. Thus, at at, is effectively constant at the integrals. And we may write this. So using the definition of redshift, we find that the redshift of light from a distant object is relatively related to the expansion factor at the time it was emitted. That is nice. I had touched upon this earlier, even though I'm still not clear on everything. But when light is emitted at that time, we see it when it was emitted, not as it is now. So the redshift would tell us the nature of the universe at that point because we can backtrack how long ago it was. Here we have used the usual convention that AT naught is 1, just like real kindness was saying. Thus, the last paragraph, if we observe a galaxy with a redshift z equals 2, we're observing it as it was when the universe had a scale factor of AT equals 1/3. The redshift we observe for a distant object depends only on the relative scale factor at the time of emission and the time of observation. It doesn't depend on how the transition between ATE and ATC was made. It doesn't matter if the expansion was gradual or abrupt. It doesn't matter if the transition was monotonic or oscillatory. All that matters is the scale factor at the time of emission and at the time of observation. And this is the scale factor at observation, and this is the scale factor at emission. So I guess it's kind of like path independent, how we would describe it in classical dynamics. So there you go. I went ahead and got through uh, the chapter 3 in 2 days. Don't understand everything completely, of course, but it does allow me to be able to start the homework and at least be aware of all the equations that's going on. Um, a good thing that Lisa had mentioned, I think I knocked my mic a bit, bring it up a bit. Good thing Lisa had mentioned was perhaps calculating or at least in some way relating the gravitational potential of the solar system in the Milky Way galaxy, similar to how we compared the gravitational potential of the Earth around the sun to calculate the speed of the sun, the speed of the Earth around the sun, and how it matched measuring the observational velocity we can get from just knowing the distance from the sun and how long we take to go around it. So it seems like that would be an interesting calculation. So I may do that. Maybe that'll be something good to do next week if nothing else comes up that's more pressing. Because I'll have to find a few things out. At least I had mentioned the time we take to go around. I guess maybe that's all we need. The distance. Oh, it's sickness. Oh, okay. Well, thanks for letting me know. Let's take a look at that. So give me a moment. Let's see how quickly I can share this link that Alicia shared. So I'll move from this. Share a window instead. And it will open in some crazy place. Right. And I could probably unshow the book image. All right, this is what we're looking at. We have Cygnus. So this is what he's named after. Oh, that was going to give me a pronunciation. Awesome. Cygnus. Right, you're right. It was more for the black hole Cygnus and the wicked tush tomb. Okay, I have to keep that in mind. I rush. Also, those typos get this today. It's awesome. So I'll keep that in mind, Cygnus. And Cygnus is such a nice guy. He didn't mind. I've been calling him kindness for like, I don't know how long. But I'll keep it in mind as Cygnus. And that project seems like a very interesting project with the uh uh calculating the gravitational potential of the galaxy and seeing if the rotation matches. So yeah, maybe I'll do that next week. So look to that. And and let me know how y'all like these long shows. Usually I go for just an hour, but I figured, hey, I got to read the book anyway. Maybe y'all will find it interesting. Y'all like these longer shows? We'll be going in more detail. Let me know. I can just go back to just hour things with more fun stuff all the time. And I think next week I'll just have my regular hour show at 8, and perhaps I'll do the uh, galaxy gravitational potential. The more I think about it, the more interesting it seems, and we'll see how that goes. So thanks, Lisa and Real Cygnus for joining. I see there was a lot of others that joined, a lot for me at least, was like 16, but only a few chat, you know how it goes. So I'm glad you enjoyed it, Lisa. So maybe once a week I'll do a longer on our website. Once a month I'll do a longer in-depth show. I'll mix them up. We'll see how it goes. Always good seeing y'all. Always good chatting with y'all. I'll be back next week, if not sooner. And look forward to doing the gravitational potential thing. I'll plan on doing that. We'll look at the gravitational potential for the galaxy. It'll be a bit more complicated because there's mass out and within. We'll see how it goes. And I hope y'all have a good evening. I'll see y'all next week.